All right, so the second part of 6.5, we're going to pick up with what's called solving a right triangle. What solving a triangle basically means to do is to find 6 things, all 3 sides and all 3 angles. Well, there's one thing that you're not going to have to find right away, and that's one of the angles, because we're dealing with a right triangle. So that means we're always going to have a what?
A 90.
Yeah, we're always going to have a 90. So there's one thing out of 6 we don't have to worry about. And in order to solve for the other sides and angles, I have to give you some information in addition to the 90. Specifically, I have to give you 2 things. So you either have to be given another angle in the problem and the length of a side in addition to the 90. Or I could give you the 2 sides. Either way, I have to give you a side. Right? You can't solve a triangle if you don't know a side, because that would be like saying to you, I'm thinking of an equilateral triangle. Here's all the angles, 60, 60, 60.
Well, it could be any side.
Tell me how big the sides are. Yeah, you can't. So you have to have one side. But you could have both. Or you could have one of the other angles. And depending on what you're given, we're going to use Pythagorean theorem, possibly, to figure out a side, if we know 2 out of 3. Or we also might use sine, cosine, and tangent to figure out a side as well. Depends on what we're given. But we're going to focus on just using sine, cosine, and tangent. We are not using secant, cosecant, and cotangent. It's not that you can't use them. It's just that calculators don't have buttons built in for cosecant, secant, and cotangent. So it's easier to stick with the 3 that they already have buttons for, and we can do everything with those 3. So keep in mind Pythagorean theorem, and the fact that when you add up all the angles in a triangle, we have to add up to 180. So if you know 2 out of 3 angles, you should be able to get the 3rd one. Pretty easy. All right. So let's try a few problems where we solve a triangle. Solve the triangle. So to do that, as I said, you're going to stick with one of those 3 functions. And the way you're going to figure out which one you need to use is you're going to draw a diagram. You're going to look at the information that you know, and then you're going to look at the information you're trying to find. Let's say you knew the opposite, and you wanted the adjacent. So now you have to think in your head, okay, what trig function has opposite and adjacent? Tangent. If you knew the opposite, and you were trying to find the hypotenuse, then you're going to think, okay, which one has opposite and hypotenuse? That's sine. So it's all about what side you know and what side you want to know. Okay, so here's our problem. They're giving us an angle, and they're giving us the length of a side. So first thing I would do is sketch it. And what do we want to give labels to this so we can keep track of things. What are the labels we use for the sides?
A, B, and C.
Yeah. We generally use an A, B, and a C. And what do we call the angle across from A and B? Beta. All right, let's fill in what we know. One angle of a right triangle measures 37. It doesn't really matter which one you call the 37. You're going to get the same 2 answers, whether you put the 37 here or here when you find the other sides. So let's, in our problem, let's call alpha the 37. And the hypotenuse, well, you don't have any choice for that. That's got to be which letter? C. Right, so sometimes what I do, I don't always do it, but a lot of times when I'm showing how to do this, I'll make a table off to the side where I put the 3 sides in one column the three angles in the other. We don't have to worry about the right angle. So A we don't know. So I'll put a box around it so I remember to find it. B I don't know. Let's see, I know. And alpha I know. That's 37. Okay, what could we find first there? We're not even really doing like trig. Really, we could just really use geometry to figure this out. Yeah, we could figure out beta. How do we get beta? So you could add 90 and 37 and subtract 180, or you could just subtract 37 from 90. Be the same. So let's just take 90, bless you, minus 37. So that means beta is 53. So that's one thing. Any question on how we got beta? All right, now we have to get A and B. Well, we can't use Pythagorean theorem because you're missing two sides. But what you can do is use an angle and then use a trig function. Now, you have two angles you could do this problem. You could use the 37, or you could use the 53. Which one do you think is better to use? Technically, yeah, it should come out the same, but I have a preference as to which one I would pick. Why would you pick alpha?
The start, I guess.
And why is it good if we knew it from the start?
Because you know it's always right.
We know that that one's right. If you use beta and you're wrong and you find everything else is going to be wrong. So now that we have the 53, we're done. We're never going to use the 53 in this problem. We're going to use the 37. And let's say we want to do A first. So this is the side that we want to know. This is the side we do know. We need to figure out the names of these two sides from the perspective of the 37. What's the side that's farthest away?
Opposite.
So this is opposite.
Sine.
And what's this one? Hypotenuse. So which trig function has opposite and hypotenuse? Yep. So we're going to use sine. So this is to find A. So it's always the sine of your angle equals sine is opposite over hypotenuse. So A over 8. And that's your equation to solve for A. Now, how would you get A by itself there? Multiply by 8. Now, in this section, we do want to round that off to 2 decimal places. So first thing you want to check is the mode on your calculator. Make sure it's in degrees. You can do these problems in radians, but I think the ones I give you are all degrees. So 8 sine 37.
Right, you said that you can be in radians, but you want degrees?
Well, I'm saying you can do these problems in radians, but I think all the ones I give you are degrees
Okay.
on the test. Yeah. But just check the number inside the parentheses and just make sure it has a degree symbol. So A is 4.815. 4.815. Okay. Now, I know 2 out of 3 of the sides. So what could I do now? I could do the Pythagorean theorem, but that's not a good idea. Why do you think I would say not to do the Pythagorean theorem? Okay, there's decimals in it, but I can use my calculator, so that's not too bad. But what's another reason? It's what? I don't know if this is right. And again, same problem if you had stuck with using beta. We don't know if it's right, so if we use it and it's wrong, then everything else is wrong. So the idea with right triangle trig is you always go back to the information that was given to find what you don't know. You never use what you find to find something else. And in right triangle trade, you can do that. In non-right triangle trade, you can't. You have to use things that you found to find other things. Which means if you mess up on one, then it's all messed up. But for this, we can get away with that. So let's find B. And this time, we're still using the 8, because that's the side that was given. But now we want to find B. So what is side B in relation to the 37? Adjacent. So no hypotenuse. We want adjacent. Which trig function is adjacent and hypotenuse?
Adjacent and hypotenuse?
Yep.
That's cosine.
That's cosine. So cosine of, what's my angle? 37 degrees. And then adjacent is B over hypotenuse is 8. And you can do the same thing you did last time. When the number is in the bottom on the other side, all you have to do is multiply both sides by the number. And that gets the letter by itself. So 8 cosine 37. 6.389. That's B. Now, if you had time and you wanted to double check your answer with Pythagorean theorem, you could. 4.815 squared plus was it 389? Yeah, 389 squared should equal 8 squared, roughly. We rounded these off, so it might come out to like 63.999 or something like that. But that's the idea of how you do a right triangle trade. Any questions on that? Okay. This is another one of the same type. Does anyone want to see one more of that type?
What do you mean that type?
This method.
What is going to change next time?
We're gonna, instead of giving you an angle and a side, I'm going to give you 2 sides instead. So this is another one where they give you an angle and a side. Anyone have a question on that type? Okay. The 2 side type is different. So let's look at that. So we're looking at the case where you're given 2 sides. So it says the hypotenuse and a leg are 12.7 and 6.1. And the directions are to solve the triangle. Okay, so let's make a sketch. Well, the hypotenuse has to be the long side, so that's the 12.7. And the 6.1, it doesn't matter where you put it. If they said like A is 6.1, then okay, you'd want to put it wherever you put A. But they didn't really say, so let's just put 6.1 here. And the labels are just there for you. Labels are basically something we just invented to keep track of things in our head. So we can put an A here, a B here, and a C. That's an alpha. And that's beta. All right, so let's make our table.
Why did we make that one A this time?
What's that?
Why did we make that one A this time?
To make it, I mean, it doesn't really matter where you put the A and the B. So I'm just going to switch it up and show you different ways of doing it. What is important is alpha is across from A and beta is across from B. We want to keep those across from each other. Okay, so the way we labeled it, do we know A?
Yes.
What is it?
6.9.
How about B? We don't know that. How about C? We know that one. Alpha and beta? We don't know. Now, there's something here that I'm okay if we do it this time, but I wasn't okay last time. What do you think I'm okay with you using now?
So
No, I still don't want you to use anything unifying to find other things. Never, don't ever want you to do that.
Okay.
Yeah, I'm okay with the Pythagorean theorem on this one.
Why didn't we want to use it last time again?
Because we didn't have two sides to do it.
I see.
Right.
Oh, I see.
This time, you're not plugging anything that wasn't given into the formula. That was all given. So let's use it and find the length of B. Now, once I get B, I don't want to use B for anything. I just want to find it and be done. So 12.7 squared equals 6.1 squared plus B squared. What's 12.7 squared? 161 point what? 29. And 6.1 squared? 37.21. Okay, I need 161.29, and I need to minus the 37.21 from that. 124.08. And the last thing I need is the square root, so 11 point something.
11.14.
11.14. Okay, so that's roughly what B is. It's about 11.14. Any question on B? Okay, so we got B. Now, we can't add the angles up and subtract from 180 to get alpha and beta because we don't have either one of them. So let's say we want to find, let's say we want to do beta. Let's do beta first. So this was to find B. So find B. And now let's find beta. It doesn't matter whether you do alpha or beta first. It's going to be the exact same amount of work. So we want to find beta, and we have to stick with the information that we were given, which means we're going to use the 6.1 and the 12.7. What is the 6.1? The name of that side relative to beta. This is adjacent. And what about the 12.7? Hypotenuse. So what trig function has adjacent and hypotenuse? Cosine, yep. And it's always the cosine of your angle. What's my angle going to be? Beta. That's where the variable is. And adjacent over hypotenuse. So I need to get beta by itself. The problem is the variable is inside of a function. So when you have a variable that's inside the argument to a function, the only way to get the variable out of the function is to cancel the function out. So like if you had a variable like square root of x equals 4, and you want to get this variable by itself, you need a function that cancels out the square root function. In this case, it would be the squaring function on both sides. So in this one, we need a function that's going to cancel out the cosine function. Well, those are reciprocals, but they don't cancel each other out.
Could we just find the cosine again or something?
So right now we have 6.1 over 12.7, okay, and that's beta. The way we're going to get rid of the cosine function is to use what's called inverse cosine. So the way you cancel out the trig function is with its inverse. And the inverse trig functions all have the symbol on the calculator with a -1 up a little bit higher. That -1 is not an exponent. The -1 is just a symbol that means inverse. That's what it is. So whether you had to cancel out sine, cosine, or tangent, you use inverse trig. There's a few different ways you can write it. Well, two that I know of. This is how most calculators do it. Sine with a -1. That's inverse sine. Or an older way sometimes you might see is arc sine. If you don't like arc sine and you see it, then just cross it out and put sine to the -1. That means inverse sine. Same thing. And remember, when you do something with a function in an equation, you do it to the entire side. So like if I had this, let's say x plus 3 equals 4. And you wanted to do the squaring function on both sides, it wouldn't be x squared plus 9 equals 16. That's not how you square both sides. That's the left squared, and that's the right squared. So that would be x squared plus 6x plus 9 equals 16. So what I'm saying is when you do a function, you have to do it to the entire side, not the individual terms on the side. You have to do it to the whole thing. So we're going to go back to the problem we had and see if we can solve it using inverse trig. So right now we have cosine of beta equals 6.1. To cancel out cosine, we're going to use inverse cosine. And the correct way to say it is you're going to say take the inverse cosine of each side. Just like if it was a square root problem, you would say take the square root of both sides. So that's how you want to say it. Take the inverse cosine of everything that's on the left. And I don't really have enough room to squeeze it in, but I'm just going to say take the inverse cosine of everything that's on the right. There is no multiplication happening right here at all. Just like if I had this. When you take the square root of both sides, putting that symbol there does not mean square root times x squared. It just means take the square root of what's below it. This means take the inverse cosine of what's next to it. So what happens is these cancel out. And the only thing you have on the left side now is beta. And on the right, it's the inverse cosine of 6.1 over 12.7.
Would that still be in brackets, or would that be in parentheses?
I mean, you could use any kind of grouping symbol you want. I just choose a bracket here because sometimes when I put two things next to each other in parentheses, people think it means multiply, but there is no multiplication happening. So second cosine is how you do the inverse cosine. You have to press second first. And then you put 6.1 divided by 12.7. So 61.29. And it's very important you put your calculator in the right mode. This is degrees. Yeah.
Is that the same as just 1 over cosine?
No. 1 over cosine would be secant. So this -1 doesn't have anything to do with flipping something. It's like the -1 is a special symbol that means inverse. So yeah, don't even think of this -1 as an exponent. It's not. I know it looks like it is. All right, so 61.29. So there's beta. Now, if I only had 5 seconds left to finish up the test, I would just subtract this from 90 and pray I got it right. But the better way to do it, so you don't rely on that answer, is the way we found beta. So let's find...
Really? Did that twice?
Let's find alpha. Okay, So we want to know this one. And we're going to use this. We're going to use that. Well, now these names don't apply anymore because you switched your angle. So now you're looking at everything from a different angle. Well, let's start with the bottom one. What's the bottom one?
Opposite.
It's opposite. I guess the hypotenuse, that one does stay the same. But the adjacent side is no longer what it was because you switched your angle. So now we need a trig function that uses opposite and hypotenuse. Sine. So it's going to be the sine of alpha equals, and what's going to be my fraction on the other side? Yep, 6.1 over 12.7. And what are we going to take on each side to get rid of sine?
Inverse of sine.
We're going to take the inverse of sine on each side. So take the inverse sine of everything that's on the left. There is no multiplication happening in that problem. Take the inverse sine of everything on the right. And we know that the angle should come out to a little less than 30, so 28 point something, based on what I got for beta. Let's see. Second sine, 6.1 divided by 12.7. 28.71. And that's how you solve a right triangle when they give you two sides. So the only time you have to use inverse trig is if you are given two sides. If you're given a side and an angle, you are not using inverse trig. Inverse trig is only for finding angles. That's it. Any question on that one? All right, so those are the two types. The only thing we didn't, let's take a look at something. So we talked about in the first type, when you had an equation where you had a number on the left, you had a letter on the top, and a number on the bottom. But what would happen if you end up with an equation? I'm just going to make this one up. 5 sine of, actually let's do it. Sine of 10 degrees equals, what if the number was in the top? You don't multiply both sides by 4. And that would just give you 16. What could you multiply both sides by this time? To at least get rid of that fraction on the right. Yep, you can multiply both sides by a. And times a. I'm just going to put a box around what we started with so you remember that was the original problem. So now you have a times the sine of 10 would equal 4. And what would be your last step to get a alone here? Yeah, so it's just algebra, but I wanted to make sure people were okay with that. So those cancel. And you get a equals 4 over the sine of 10. So look at the final answer and look at what you started with. Does anyone see what ends up happening with letters in the bottom? Yeah, all you have to do is swap these two things. So whenever you have an equation, like if you had 3 equals 5 over x, and you're trying to find the answer, well, it's x equals 5/3. You can always swap in that type of equation what's in the bottom and what's on the other side. And the reason why is what I tried to teach. So not really trig, but more algebra. Any question on that kind of idea? Okay, so we looked at the side and the angle. We looked at the side and the side. This is another problem I had with a side and a side again. Does anyone want to see another one with side and side? Well, how would you get the third side? You could do Pythagorean theorem. Yep. And are you going to end up using inverse trig here or no?
Yes.
Yes.
Twice.
Yes, you're going to have to do it twice. Again, if you were running out of time, you can do it once, subtract from 90, and hope you got the first one right. Are there any questions on the side case?
I might want to go back to it if we don't. If we have extra time.
All right. We're not doing that. Skip that. Skip that. Oh, let's see if we can do this one. Find the 6 trig values. This is kind of like last night now. So we're not actually solving a triangle. We're going to draw a triangle. But we're going to find the sine, the cosine, the tangent, the cosecant, the secant, and the cotangent. It says find the 6 trig functions of an angle where the point 2, 3 is on the terminal side. Okay. Let's draw it. Hello? Try to make my grid a little bigger for you. See if I can. I think I can fit it over there. So it says the point 2, 3 is on the terminal side. Okay. So 2, 3 is on the terminal side of my angle. So I have an angle, essentially, like that. And I'll draw it in red so you can see it.
Sorry, what was the full question?
Find the 6 trig functions of the angle where 2, 3 is on the terminal side. So any questions on the picture? So we got a point 2, 3, and the terminal side goes right through it. And I want you to find the 6 trig functions of that angle. Well, in order to do that, we need to make a triangle in that picture. Does anybody have an idea how I'm going to make a triangle? Having something to do with the point 2, 3, and we need to make a third side. Yeah?
Could you draw directly down from the point 2, 3?
Yeah. Just draw it directly down from the point 2, 3. Now, you don't have to do it from the point 2, 3. Because remember, we said about triangles. Right? If they're similar, does the size of the triangle matter? No. But 2, 3 is probably the smallest one you could do, where the sides are still nice numbers. I mean, you could do 1, 1.5, but why do that? So this is 2. This is 3. And what would my hypotenuse be? Square root of 9 plus 4, which is 13. Yep. And you're just doing what we did yesterday. So what's the sign in that one? So 3 root 13 over 13. So you remember, you're not solving for theta. That's what we did in the last problem. You're just writing the trig functions. How about the cosine?
2 root 13.
Yep. Kind of like a review question. How about the tangent?
3 over 2.
3 over 2. Good. How about the cotangent?
2 over 3.
I just like to get the ones out of the way that don't have square roots now. What about the cosecant? That's hypotenuse over opposite. And the secant?
13
Square root of 13 over 2. So any questions on, and maybe I should have put down what these were originally. So the sine was 3 over square root 13, and then we fixed it. And this was 2 over the square root of 13, and then we fixed it. Any question on finding the 6 trig functions? Okay. So now, let's solve for the angle in the last problem. Now, this is more like what we learned today. Any one of these pieces of information will help you to solve for the angle. They all have theta in the equation. If I was going to pick one, I generally solve the equation that has sine. That's the one that I would pick. So let's copy that down to the other page. Sine theta equals, was it 3 root 13 over 13?
Yes.
Okay. So how are you going to solve that equation and get theta itself?
Alright, so why did you choose sine? Just because that's what you do.
Yeah, I would just choose sine.
Yeah.
Not that the other ones are wrong. But first of all, we don't even have buttons on the calculator for inverse secant, inverse cosecant, inverse cotangent. So I definitely wouldn't choose those.
Yeah, okay.
But
Inverse sine.
yeah, we're going to take the inverse sine of what's on the left, and we're going to take the inverse sine of what's on the right. And now we're solving for the actual angle in the last problem. So inverse sine, it's actually probably easier to type it in as 3 over square root of 13. I think that's less buttons than having to type all of this in. And if you're doing inverse trig, it's fine to have a square root in the bottom because that's not your final answer. It's just what you're plugging in to get the final answer. So we get an angle of 56.31. Any question on how we solved for that angle?
That was just like going back to a part of what we did in the last problem.
Yeah, we only used the first equation. If you did the inverse cosine of each side on the second one, you would have gotten 56.31. And let's try the inverse tangent of 1.5. Second, inverse tangent of 1.5. 56.31. So you can use any of them. But there's a reason why I'm saying to use sine. And you'll see right now. Any other questions on how we got that? Okay. So we know because the point was 2, 3, right 2, up 3, we know that the angle we were looking for had to be in the first quadrant. All the angles in the first quadrant are between 0 and how much? 90. Now, let's say we were looking for the point, let me get a grid up here again. Let's say I gave you the point -2, 3. You might think, well, isn't that just the same angle? Not quite. Left 2, up 3. There's your terminal side. Like that. Here's your initial side. What you're looking for this time is this angle right there. It's in quadrant 2. So we know it's going to be between 90 and 180. But the way you find it is you make a triangle just like you did before, and that's exactly the same triangle that we had in this problem, except the triangle has been flipped. This is 2, this is 3. So what we do is we still solve for this angle that I'm pointing to right there first. That angle is called our reference angle. When we're in quadrant 1, the reference angle is the answer to the problem. You don't have to do anything else. But when you're in quadrant 2, if you knew this angle right here, how would you get that angle right there?
180 minus the angle we have.
Yes, you would do 180 minus what we call the reference angle. Now, while we're kind of looking at it, let's draw the same kind of diagram again. But let's say it was this. You're still working with the same reference angle. Left 2, down 3. Here's your terminal side. Here's your initial side. This is what I want to know this time. If you make your triangle, this is 2, this is 3, you're still going to be finding this reference angle right there, which we already know is 56.31, I think.
Yeah.
If you're in quadrant 3, what do you think you would do with your reference angle to get this entire angle?
Subtract from 360.
Would you add, would
277.
you add it to 180?
You would add it to 180 because you've gone this far to get to quadrant 3, but then you've gone this much more past 180.
I think you subtracted from 270 as well.
No, because that would mean you would know this, and you don't know that. That's the complement to your reference angle, but we don't think of it that way. So your reference angle, you could add it to 180, or what you said, you could subtract the complement of your reference angle to 270, but that confuses me. So we're just going to think of it as adding it to 180. Now, let's say you had the same kind of thing, except let's go to -3. Again, the reference angle in this problem is the same as all the other ones. 2, -3. Terminal side, initial side. I want to know that. If you make your triangle, this is 2, this is 3, you're going to be able to figure what I'm pointing to out. That's your reference angle. If you knew this angle, how would you find that one?
You added 270.
Adding to 270 would mean you know this.
360
yeah.
minus the angle.
360 minus that angle. Yeah.
Yep.
To add it to 270, you would need to know this.
Yeah.
Then you could go past 270. But we're going to go before 360. So I'm gonna write that down, but I wanted to kind of show you in a diagram first the idea of what's called a reference angle. The way you always find the reference angle is to use inverse sine. That's why I said to you, when we solved that last problem, you could have done inverse cosine or inverse tangent. But I said to use inverse sine, and that's because of this. If you use inverse cosine and inverse tangent, you can still do the problem, but sometimes weird things happen. So stick with using inverse sine to find your reference angle. And specifically, the absolute value. Reference angles, you can think of them as like a distance. It's measuring something. We don't want to think of this as a negative number. That will confuse us more. The last thing. I actually already did the next question, but we'll do it a little more formally. So to find your reference angle, we're always going to use inverse sine, and whatever you get, that angle needs to be a positive number. So if you get a negative number, when I ask you for the reference angle, just take the absolute value. If you're in quadrant 1, you're done. The reference angle is the answer to the question.
Is this all for finding reference angles?
Just the inverse sine. That's how you find the reference angle. But the reference angle itself is not the answer in quadrants 2, 3, and 4. It's what you guys just said. If you're in quadrant 2, how you know you're in quadrant 2, your x-coordinate would be negative and your y would be positive. You have to find your reference angle and subtract it from 180. If you're in quadrant 3, you're going to draw a triangle, you're going to find an angle, and that angle needs to be added to 180. And if you're in quadrant 4, you're going to draw a triangle, find the reference angle, and that needs to be subtracted from 360. And it seemed like when I do the pictures, most people, I didn't tell you, eventually figured out, add it to 180, subtract it from 180. So you can visualize it if you forget, wait, I'm in quadrant 3, what do I do? You can draw it and kind of figure it out. The reference angle is the angle in the triangle that's tucked up towards the origin. That's your reference angle. Right, and we'll do one of the ones we already did, but I'll kind of write the whole thing out. Okay, does everybody have those three?
Last one, 360.
360 minus the reference angle. Now, if you're doing radians, change 180 to pi and change 360 to 2 pi. But it's easier to grasp the concept in degrees, so that's why I teach it in degrees. So let's do 2, negative 3. So the point 2, negative 3 is going to be on the terminal side. So draw your terminal side. Initial side is always on the positive x-axis. And this is the question. What quadrant is... oh, wait a minute. I'm going to change that to actually do this problem. Let's make it negative 2, negative 3. What quadrant is negative 2, negative 3? 3. So I'm looking for an answer between 180 and 270. I'm going to draw my triangle. Just like that. This side is 2. That side's 3. And what did we say the hypotenuse was? Square root of 13. This 2, 3, root 13. It's the same triangle that we did in this problem. It's just flipped. So let's find our reference angle. So I usually use theta to represent my reference angle. Did they say to already use theta for something else in this problem? Oh, they did. Okay. I don't know then. I'll just call it alpha. Because when they say find theta, they already use that letter to represent this big angle. So pick a different. Okay. What trig function did I say to use to find your reference angle? Sine. So we need sine of alpha equals, how long is the side opposite? 3. And the hypotenuse. What's the hypotenuse? Root 13, yep. And now you're going to solve for this angle right there. That's what you're going to find. That's not your answer. It's what we're going to use to get it. So how am I going to get rid of sine? Yep, and we've already done this in the last problem. Inverse sine of 3 over the square root of 13 is 56.31. So alpha is 56.31. So how am I going to get that?
Wait, sorry, how did we know that?
Right, we're in the third quadrant. So we know we've gone at least 180, but we've gone past it exactly alpha units. That's how much past it we've gone. So 180 plus my reference angle. That's why quadrant 3 is 180 plus reference angle. So what is 180 plus 56.31?
236.
236.31. And that's the angle that they wanted in this problem.
And you did that by adding 180 to that.
We added 180 to our reference angle. Yep. So when you draw your triangle, doesn't matter what quadrant you end up in, the reference angle is always the angle right there. It's the angle between the hypotenuse and the x-axis. I guess you could think of it that way. The reference angle is the angle between the hypotenuse and the x-axis. Question on that? What's your formula in quadrant 2? This is 3.
181.
180 minus the reference angle. What's your formula in quadrant 4? 360 minus it. And what about quadrant 1?
It's just the inverse side.
It's just the inverse side. It's just the reference angle. Quadrant 1's the easiest one. Yep. All right. I think last thing. I think we already mentioned this before, but if we have angles that are 0, 90, 180, or 270, then from doing the unit circle, we know all the trig functions come out to either 1, 0, -1, or undefined. We did this when we talked about the unit circle, so I don't think that's anything. All right, now, I'll show you one last thing on the calculator. Let me take the sine of 30, and I get that. Now let me take the sine of 150, and I get that. So if I do the inverse sine of 0.5, what am I going to get? $30?
But couldn't you also get 150 technically?
Yeah, you could get 150, but the calculator is not going to tell you it's 150.
It's going to give you the smallest one.
So yeah, it's always going to give you basically the answer that's for sine. It's going to give you the one that's in quadrant 1 in this case. Now, if I did, say, cosine of 70, I get that. Now, I could also do, I need to think through it. 360 minus 70. I could do the cosine of, and if I did my math right, 290 comes out exactly the same. So if I do the inverse cosine of 0.34202, the problem is it's only going to give me one of those angles, and it chose to give me the 70. It did not give me the 290. So how am I getting this other one? What am I doing in my head when I kind of think through it? I'm going to show you what I did.
We need this? Is this something that I
Yes.
utilize?
Yes. So this is a diagram that shows you where the trig functions come out positive. A stands for all, S stands for sine, T stands for tangent, and C stands for cosine. So if you give me an angle that is between 0 and 90 degrees, I know that if I take the sine, the cosine, or the tangent of it, they all come out positive. If you gave me, let's say, 150 degrees, what quadrant is 150 degrees in?
Just 2.
It's in quadrant 2. So I know that if I take the sine of 150 degrees, it will come out positive. Everything else will come out negative in that quadrant. Cosine and the tangent. Give me an angle that would be in quadrant 3. 200. I don't know what the sine or the cosine or the tangent is of 200, but I do know if you take the tangent of 200, it will come out positive. The sine will come out negative, and so will the cosine. How about an angle in quadrant 4? 315. If you take the cosine of 315, it will come out positive. The sine of 315 is negative, and so is the tangent. So all this does is tell you where certain trig functions come out positive, and if it's not positive, well, the only other choice is it's negative. And the way I remember this diagram is I usually refer to it as the ASTC diagram. ASTC. All students take calculus. ASTC. Whatever you want to use to try to remember. All calculus teachers, smart. I don't know. Something. But ASTC. And the letter tells you the trig function that comes out positive in that quadrant. So using this combined with that reference angle formula, those two things we're going to use almost every day in trig when we get later on. Okay, any questions on that chart? Okay. So, I need to change just a couple problems. So 25 to 34, that's okay. 5.
Mr. Hager, 33 and 34, we can make the inverse of secant and
so 33, yeah, we'll just skip those two for now. So 25 to 32, that should be okay. 40 to 42, that's okay. 45, yep, that's fine. 49 to 53, that's okay. And then 57 and 61, we're not going to worry about those. Okay, so it's 25 to 32, 40 to 42, 45 and 49 to 53 are.
Max. Wait, Max was close to Max. Is that you that's a father? That was you. I don't know why.